The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Good afternoon. I'd like to present you basically a study which has been done over the last years by Keisuke Takahashi, who used to be a PhD student of mine, who actually got his PhD last November on the subject. And we were looking into how pumping affects the properties of self-compacting concrete. And we came to this because we had experiences about 8 to 10 years ago with pumping concrete. We did some field trials. We also looked into literature to see on changes on rheological properties of concrete, and based on this we designed our study, which basically was on a self-compacting mortar in order to be able to measure some parameters which are difficult to measure on the concrete itself. And there we looked into two aspects. One aspect is what I call the macro level, which is our technological properties, workability and rheological properties. And the second one is the micro level. This is an area where we see what happens to the cement particles. How is hydration affected by this pumping process? And then I'd like to present you a concept as a summary, or a concept and a summary. But let's start with these field trials. I'm coming from a town in Germany which is called Freiberg, often confused with Freiburg, which is a very famous university. We are basically a mining university, and there we have the opportunity to work underground. There is still an old hard rock mine, and it's usable up to 150 meters down. And at this depth, we excavated a void which corresponds a little bit to an escape tunnel of the German railways. And in this void, we pumped concrete in order to make the shell. So you see here on this slide the concrete truck which comes. It's placed in a hopper of a pump, and then it's pumped underground. You see the construction site underground, the mold in the background, and here you see also a little bit this part where the concrete goes this 150 meters down in free fall. Then it has to pass through an elbow, and then it's pumped another 70 meters to this site. And we experienced problems, of course. We experienced problems with separation. We had also sometimes to take everything apart, which is not very nice if you are underground, but at least it's not hot there. Average temperature 4 degrees centigrade constantly. We did some measurements, exactly what we saw before, but not on a large scale. But we also qualified each truck which came in terms of slump and slump flow time. And you see here values on mixed designs based on an ordinary cement, a SEM1 type, and on a SEM2 type, above ground and underground. And you see, for example, for the above ground measurements, this is the black line. If we go then underground, we had changes in the slump value. If we go to the SEM2 cement, these changes were more pronounced. And the same we have for the slump time, or for the T50 time. And there we saw, for example, a segregation, or at least something which we could qualify as a much faster passing through this V funnel, which is used to characterize this flow time. Second thing was then, if you look into literature, there have been publications, also presentations in this country, also by Loke and Schiesel from Munich University, and they basically looked into the effect of mixing. Mixing self-compacting concrete with different speed and also with different time, or for different times, and then they were qualifying it by the slump value, and you see the slump value can behave quite good. It goes up in the beginning and then you reach a stable value, but sometimes you also experience situations where with increasing flowing mixing time the slump goes down, or with constant mixing times increasing also the rotational speed of your mixer, the slump would go down. So we looked also in this situation, and the first question we were asking us is what is affecting these changes. So we worked on a grout, on a mortar basically, which was consisted of Portland cement, of sand, plus plasticizer, a PCE, and a stabilizer, and in this material which corresponded to a real material sold by UB Industries was also something additional in order to affect certain shrinkage compensation. These were pumped with a snake pump for various distances, and then we made also trials in the laboratory where we were just mixing this mortar, or where we are just pressurizing this mortar. And we did this because we wanted to see what's the influence on the changes in properties. So you see here pumping, in this case, moderate distances of 50 or 100 meters. Mixing, we had a general mixing time which was 2 minutes, but then we extended it to 3 and 5 minutes additionally. We put it under pressure, you see 2 and 3 megapascals. And then we also looked into what happens if we just let this mortar after mixing sit after the times which correspond to the additional mixing times we had. And if we do this, we can first measure the flow curves. Basically, we increase the shear rate to, in this case, 100, and then we decrease it again. And you see for the long pumping distances, if you compare here, this is the red curve, which corresponds to the 7-minute mixing, 2 minutes plus these additional 5 minutes. Then we see similar effects on the rheological parameters of the material. And these results we depict in Rheographs. This is shown in several publications which you see in the literature by Wallevik, and you see we basically took a reference point which we call 1 or 100%, and if we depict flow value as a function of the flow time in the J14 funnel, this is now to the Japanese standards, because Mr. Takahashi, or Dr. Takahashi was doing it, or we are calculating yield stress and plastic viscosity. And if you look at this, then we see that either mixing or pumping exerted the most pronounced effect. The simple pressurization or letting the material just sit did not have the same pronounced effects. So from this point of view, we think that shear stress, which is in a pipe, especially also with different friction coefficients at the outside, or which is introduced by your mixing tool, by your paddle, this changes somehow the rheological properties. And the question is, what is this change? And since we are at university, so we try to understand what's happening in terms of hydration, what is in terms of chemical processes. So here you see first a general idea of hydration, and it's used as a calorimetry curve. So you measure the temperature as a function of time, and it's possible because it's an exothermal reaction. So if something is happening chemically, you will see it here. And the first thing which you see is in this alpha and beta, which we call induction or pre-induction period. We have a dissolution of ions. These ions will increase or change the concentration around the cement particles is one thing. The second thing, it will already start to make prehydrates or precursors, which are shown as these small green dots. This is two theories which you find. Sometimes people are fighting each other, saying one theory is right or the other one is right. Probably both mechanisms should be taken into account. And after this constellation, after this, which happens in the first 2 or 3 minutes, then you get some time. Here you see as an example up to 12 hours. And during this time, the prehydrates will go over to real hydrates. Also calcium hydroxide will be deposited or will nucleate in this area, because you have a critical saturation or supersaturation of calcium in your solution. At the same time, you see these needle-like crystals. They will interlock, and you have as a technological property the end of workability and the increase in mechanical strength. So we did this type of measurements for our systems. As you remember, we had here 1 minute, 2 minute, 7 minute mixing, and if we increase this mixing, we see basically first that this prehydration period is more intense. So we have a stronger dissolution of ions in this first part. The second thing is the major hydration, which means the stiffening, which we influence, moves to shorter times. So we accelerate the hydration, and the third thing what we observe is that this peak, this major peak, which corresponds to the massive precipitation, increases in intensity. So we really see we change not only the state of dispersion, but we also change the hydration, we change the kinetics, if you allow me this expression, of hydration. And then we had a third point. There we were looking what happens with our superplasticizer, our PCE. So we measured the concentration or the amount of superplasticizer. This is basically the black curves, or this black axis, in milligrams per gram in the solution. We measured as well the specific surface area as a BET surface area of the particles which were in the solution. So it was basically centrifuged and still in the wet state or in the liquid state. And on these particles we measured the specific surface area. And then we calculated the amount of PCE per unit of specific surface area to get an idea how much superplasticizer could have been adsorbed. And then we see basically the specific surface area increases, and we see this here as a function of the mixing time. So the longer we mix, the higher our surface area, indication that we create more hydrates, and also the higher the adsorption of PCE, but per unit area of these hydrates formed, it decreases. So we might end up with not enough superplasticizer available to adsorb and to cause the dispersion. We did, by the way, but I could not show it here, super dosage of PCE, and then this effect is not as pronounced. So we basically think what's happening is the following. we have a self-compacting mortar or a self-compacting concrete, we add these plasticizers in order to reduce water, but also in order to get a good workability. And this super plasticizer will adsorb on the surfaces, and in this case, with a steric interaction, will allow a dispersion of the particles. Now we mix more, so we shear off particles, or we change the concentration of our solution around the cement particles, but these particles have already adsorbed this super plasticizer, so they are sheared off or scraped off, and they still, and they still have the super plasticizer on top. These small green, how to call it, spiky things with the super plasticizer on it. Now it turns from red to blue, which means it became inactive for the dispersion of the particles. And as we go on with this process, with a long mixing period or with long pumping distances, then there will not be enough active PCE in the solution, and in the end we will measure a decrease in dispersion or in rheological properties. So to summarize this a little bit, we started off by observing either when we were mixing or when we were pumping. When we were mixing for long times or over mixing, when we were pumping for long distances, then we saw that we have first a dispersion of the particles, which means good workability, but at one point in time we have negative effects, which we think might be a destruction of superficial layers, which was the idea which we had in earlier investigations. So we looked on a micro level into hydration kinetics in the adsorption of PCE on the surfaces, and also in a microstructural development, which I could unfortunately not present here. And as a consequence, we have a loss in fluidity, and we also have an accelerated hydration. So we measure, for example, also higher short-term strengths. We also would measure an increase in temperature, and we also would measure a change in early shrinkage. So this extended mixing or pumping means that our rheological properties decrease, yield stress flow value and viscosity, and the efflux time increase. If we use the Rheographs, then we think that we come to this point that the shear stress is major responsible, or in majority responsible for this phenomena, and on a microstructural level this leads on the consumption of active PCE, which is a solution which can adsorb on the surfaces, and the surfaces, however, they increase by this accelerated hydration, and subsequently we have a decrease in PCE which is absorbed on these surfaces. And this explains a little bit that we have different states of dispersion as we go along in time during mixing. And I thank you very much for your attention.